Hi guys, it's me again. This is the second part of our Fault Loop Impedance session, and the idea is to look at fault currents and the importance of the right level of fault loop impedance in order to provide a satisfactory fault current to clear our circuit protective device. So let's have a quick recap of what we have here. So this is our secondary winding within our substation. So this winding here, this is our secondary, 230 volts, and this would come through, out of the sub, and along the ground into our electricity board cutout. This would be in the premises. So when we say ground, in the towns and cities this would be buried underground, low voltage, probably part of a three-phase distribution. Or in the country, it may be overhead, coming off a pole after a transformer. So this is our electricity board cutout. So we're right in there, cutout. This is the fuse generally before the electricity meter. So this is electricity board fuse. It's known in the trade, and this is the fuse that we aren't allowed to tamper with. So we have a boundary here, pretty much. Everything that's this side, so the left side, is the property of the electricity supplier, and everything that's this side is the consumer's responsibility. So this is the bit that we can change and we can get right. Obviously we can put things, engineer cable sizes to achieve certain currents, etc. Now, after we've gone through our electricity meter, we would go through a circuit breaker or protective device, the consumer's fuse. There may be multiple fuses. So, for example, in a big installation, there may be up to 4, 5, 6, 7 protective devices all in series. And it's important that we discriminate between these devices so we get the right fuse to actually, fuse or circuit breaker to actually fail, to operate. And that's quite important. And that's another part of the design that we'll be looking at in due course. So, going back to our drawing, there's our cutout. Circuit protective, circuit protective device here, and this is our line, our R1, so this is our line cable. The load would be connected about here, so this simulates a fault. So here we have at this point, we have a line to earth connection. Okay, so that is where our live part is in touch with our earth. And what we want to happen here is we want this live current, this fault current, to travel down our circuit protector conductor, which is our CPC, which is our R2, to go to our main earthing terminal, our installation, and then outside. So then we go down the distributor's earth all the way back, probably on a lead sheath, because this is a TNS. It's a TNS arrangement because we've got a separate earth. Back to our substation, and then back again in bigger force and round, and it basically gets bigger and bigger and bigger, the current, okay, until ultimately one of the protective devices in the line and the right protective device in the line operates to disconnect the fault. Okay, so the problems we've got then, if we leave this fault, this amount of current in this circuit for any short period of time, and I'm talking about seconds really now, then we would probably have a fire on our hands. We'd have severe thermal effects. This particular type cabling is probably designed to take continuously 20-30 amps depending on its size. For example, a 2.5mm squared copper conductor can carry round about, on average, 19 amps continuously before it starts to break down and basically overheat, catch fire. So we want this fault current to be cleared as quickly as possible. And also, while the fault current is there, so while we have 270, say, amps flowing down our earth, the entire earth within the installation has that potential. So the earth potential rises as well throughout the building. So there's a number of factors here that's because of this earth fault that that we need to consider. So why is it 270.59 amps? Well, it's quite easy. If we look at the earth fault loop impedance formula, so ZS, ZE plus R1, R2. ZE is our external earth, and our R1, R2 is our final circuit resistance of our conductors from our fuse at the origin all the way back pretty much to where the furthest point on the circuit to where the load possible fault would be. So 0.35 ohms, that's our ZE. We can't change that, that's the electricity board's external impedance. I have had problems in the past when I've been on site and we've measured this using an earth fault loop impedance tester, and we've discovered very, very high levels of impedance to the point where we've actually reported it to the electricity board, who put it on their ticket system to investigate and find out what the problem is. I imagine it would probably be down to high resistance in cable joints, poor joints full of water ingress, which is limited, causing obviously adding to the overall resistance of this particular loop. Okay, so 0.35 is our ZE, our R1, R2, 0.2, 0.3, that's what we're given, that's what we've measured, so our total impedance is 0.85 ohms. Now the ZE can either be measured using a direct measurement using an earth fault loop impedance tester. It's a live test, so we need to be cautious how we do that. Or it can be obtained by inquiry from the electricity board, which is something I've never personally done. I'd imagine for design engineers who are building or designing installations retrospectively before the obviously before anything's built, they're doing it per pure design, then that information would be quite valuable to determine the exact size of cabling required in order to hit our resistance values. So 0.85 ohms, we can see there, the 0.2, 0.3 ohms on the R1, R2, we have the facility here, the autonomy to select this cable size to whatever we want it to be. So if we double this cable size, so in other words if we increase the cross-sectional area, then we could say that we would halve this resistance, so 0.1, 0.15. If we halve the resistance here, then we're going to reduce the impedance. And now looking at Ohm's law, if I move this down here, we can see that the fault current is worked out pretty much using Ohm's law, V over R. Instead, it's obviously with me in AC, we're using phased line to earth volts, 230 volts, over our calculated impedance of 0.85, so we get a fault current of 270.59 amps, which is what we have here. Now if we reduce that impedance, so if we half it, then we would actually double the amount of fault current. So what that means is the lower the impedance, and this is proportional, this is classic Ohm's law, so as the voltage is the same, it's constant, so the value of fault current is proportional to the impedance of the circuit. So the lower the impedance, the higher the fault current. And I've just put a note on the bottom there that 270.59 amps will flow during a fault until the protective device ruptures, or in a worst case, the conductors melt. But if that's the case, the conductors are surrounded by PVC, so you would probably have a fire on your hands. So we don't really want that. Okay, so let's look at an example. We have a motor. Okay, so hi guys, it's me again. We're going to look at an example now. We have a motor circuit that has an R1, R2 value of about 1.55 ohms. Now that's quite high, it's 1.55 ohms. That's quite a long length of cable, so we're probably looking at an installation, some kind of factory, or where there's a long run of cable there. It's protected by a BS88, which is a cartridge fuse. It's a HBC, it's a high rupturing fuse. 20 amp, obviously 230 volts, so it's single phase. The disconnection time in the wiring regulations is 0.4 seconds. Okay, so we've got a 0.4 second disconnection time there, so let's put 0.4. So we're going to determine if this circuit complies. Now the ZE is given as 0.45. Now that could have been measured, or it could have been just read from the previous test results, if there were any, or by inquiry to electricity board. So our earth fault loop impedance ZS is ZE plus R1 R2. So that gives us a total impedance of 2 ohms, which gives us a fault current of 115 amps. Okay, so it's quite, in terms of, it's quite a high impedance is that. So 2 ohms, if I was testing that circuit, I would have alarm bells ringing at that, because 2 ohms is quite a high value. Okay, now what we have here is, this is a time current graph from the wiring regulations. It's from Appendix 3. It's a log graph, so don't be put off by it. These are actual curves here of protective devices. So what they've done is they've turned the current up, they've turned the timed it, and every time the fuse blew at a certain value, at a certain time, they record it and plotted these curves. So they've gone through quite a few fuses really to develop this, but these are found in the back of the regs. Okay, what this means then is, you can see on here, you can see these are the different types of fuse ratings. You can see the faster the disconnection time, the higher the current. So for 0.1 we need 175 amps, and for obviously hours we need 130 amps. Now because we've got 115 amps from our impedance, which we've calculated previously, this circuit actually fails. It doesn't meet the requirements, because the actual disconnection time, if I plot that off there, this is where you need a ruler. So I go up 115, when it hits the 20 amp, I go across, I get a 1 second, which basically means it fails. So what we do is, using the resistivity formula, how can we do it to raise the fault current? Well, we reduce the R1 R2 value, so we increase the CSA of the cable. So if we double the area, we halve the resistance. So let's have a look then. So what we're going to do is, we're going to get our change our cables, double our cables up, maybe we want them in parallel, but we'll just make them bigger for now. Divide it by 2, so now our R1 R2, our ZE would stay the same, that won't change. Our new impedance is 0.775. Bit of Ohm's law now, put our new value of ZS in, and you can see the fault current now is a lot bigger, 296 amps, 297 if we round it up. It's seriously increased, yeah, it's got quite big. Now what happens here, interestingly, is you can see now that I've put on there the 160, got interrupted by the cuckoo clock there, sorry about that. So you can see there 160 amps there, where that blue line is, that is where it roughly blows. But because we've got our line here at 296, it's well past the 20, that means that the fuse is instant. So if your current is greater than the curve, then that means that the protected device operates instantly, 0.01 seconds. So just to summarise then, so by increasing the cable size of the line, R1 or R2, or both, the resistance will decrease. This will raise the fault current level, and it's basically Ohm's law. So now the circuit complies. So what you would do in reality is, if this was a situation on site, you could either look at changing the type of protective device, because obviously different protective devices have different characteristics, or you might just simply put a bigger earth in. So sometimes you come across circuits where electricians basically put in quite a lot of earths, you know, or just quite a nice big size R2 to bring that right down. So like on this example there, if we obviously put a bigger cable size and we could get that R2 down to 0.1, that would make an even bigger difference on our current. Okay, so what we'll do next is I'll go through another example with you, part 3, and we'll just see if it makes things a little bit more clear for you. So I hope you found that useful. Okay, thank you.